So today we will study a very brief concept of reinforcement learning. So let's see what is the reinforcement learning first. Okay. So far we mainly study supervised or unsupervised learning, right? So given input and output, your network outputs something, and then we compute loss function between a output and target in case of supervised learning, and then we just backpropagate, that's all. So that means, in short, minimize distance between outputs and targets. And there are two requirements for this supervised learning. The first one is targets for all inputs in the data set. We need targets for all inputs in the data set so that we can use targets to compute loss function, and then gradient can be backpropagated. Second requirement is differentiable loss function. So the neural network forward pass is differentiable, and then when computing loss function computation needs to be also differentiable so that gradient can be backpropagated to the weights of the neural network. So these are two requirements for the supervised learning. We need targets for all inputs in the data set, and loss functions should be differentiable. And these are just typical machine learning problems, like object detection satisfy such requirement, but not in some cases. So most of the tasks that we learned so far, like 3D reconstruction, SFM, all this stuff satisfy these ones. We have targets for all inputs, and loss function is differentiable, so that we can rely on supervised learning. But in some cases, that's not it, unfortunately. So that the first requirement, data collection, in some cases, data collection is almost impossible. For example, games. So, there can be many, very roughly saying, there can be many possible combinations of state and action combination for games. Go, or this is the StarCraft. We have some unit, and then each unit can locate at some position, and each unit can perform some different actions. So there can be too many possibility of combination, right? The number of S and number of A, and then the A depends on previous history. So there are too many, we need too many data, so that collecting sufficient amount of data for some task might be almost impossible. And the game is the one example. For combinations of character position or status, we can't get desired user input. So desired user input depends on so many things, including history of the play, so that makes data collection too difficult. That is the one reason why we need reinforcement learning. And robots as well. So for all joint rotation and global position of robots, there are too many desired robot actions, right? We can't get all possible amount of rotation and position and action. All this combination we cannot get all these possible combinations of robot data. That is also why we need reinforcement learning in terms of data collection difficulty in both game and robots. In particular, robot behavior, RGB videos, actually they are both temporal signals, right? Video, robots, they are in temporal space. But in image or video, we have video generated model, which is trained on a huge amount of video. So what is difference? RGB video, robot behavior, I think both are in temporal space. But then in case of video, we have huge amount of data. We have digitalized billion scale videos on the web, in the social media. We have huge amount of videos. They are already digitalized. Robot behavior, we do not have large-scale digitalized robot behavior data, right? So that is consistent with the previous time. So that is the reason why people use physics-based simulator instead of supervised learning to train robot policy network. So in short, data collection is, much more difficult. Video, we already have huge amount of digitalized videos on the web, in social media. But on robots, we do not have large-scale digitalized robot behavior data. So that is about data collection. And another thing is the differentiable loss function. So robot learning, loss function are mostly non-differentiable. That is also why we need reinforcement learning. So during the training, robot policy network outputs some robot actions. And we need to apply such action through physics simulator, right? So let's see some network and some status of robot is passed to the network and then output some action. I mean, status means just let's say some motion of some pose of robots. What this robot is doing. Let's roughly define status robot as what this robot is doing. And based on what robot is doing, maybe network can output what robot needs to do. That is action. So robot is just walking, and there is some barrier in front of robot. Barrier. It's also barrier. Their barrier is in front of robot. Then action might be detour. Right? It needs to avoid collision between robot and obstacle, so that it needs to detour. That is desired action. But we need to apply this kind of action during the training through physics-based simulator. Because for the physics constraint, if we just simply apply this kind of action to robots without physics simulator, then the robot might violate physics law, so that the trained police network might not useful. So the robot action should always follow physics law, because the robots will always be in a real world, which is governed by physics law. So instead of directly applying this estimated action to robots, we need to apply this action indirectly. We need to pass this action to physics simulator, and then physics simulator will control the robots. And so that is the reason why we need to apply such actions through physics simulator, like Isaac sim, for physics constraint. We need to always follow physics constraint. And one widely used way for physics constraint is using physics simulator, so that we can apply these estimated actions indirectly instead of directly applying to robots. So that means here, S in is S out, S in, or output and robot input state of robots. So network takes status in, input status, and then network outputs some action. And then we pass this action to simulator, and the simulator returns status output status. That is the typical thing which is happening in robot training. So that we do not use network's output directly to get S out. We always use physics simulator to get S out. So the network output is indirectly used when controlling robots during the training or inference as well. So during network, net is differentiable. We always know network is differentiable. But the physics simulator here, this is not differentiable. That is the problem. Physics simulator, Isaac sim, Isaac gym, Isaac lab, Genesis, all this stuff are non-differentiable. So that differentiable loss function, we need two requirements for the supervised learning: targets of data inputs and differentiable loss function. But here, physics simulator is not differentiable, so that all the loss function applied on S out is not differentiable. That makes problem. That makes supervised learning not applicable for the robot training. So given non-differentiable output function, how can we optimize weights in network? That is the problem. Very similar thing is happening in human motion animation. But human motion animation, most applications are in virtual space, not physics space. Like we can render some animated human in screen space, not in real world space, so that for the rendering, the characters do not need to follow physics law, so that we simply apply network's output to human motion, so that human can be animated without physics simulator. But in robots, it always in our real world, so that it needs to always satisfy physics law. The way how we constrain robots to follow physics law is using physics simulator. we pass network's output to simulator, which is based on physics, and then simulator outputs robot's status output. So let's say action might be turn right. Let's say turn right, or turn right, and go 1 meter. We should not apply this one to robots directly. Maybe we can. In case of human, virtual space computer graphics, we still use, we do not use physics simulator. We just use this action directly to human, so the human can just turn right and go 1 meter, that's all. But robots, we need to apply this one in the physics space, so that we need to apply this estimated action in physics simulator. And the physics simulator is not differentiable. That is the problem. So there are two things why we need to try RL in robot training. Of course, some recent methods do not apply RL. Some methods try to use vision language action model instead of RL, but are still widely used. RL is still widely used, and so you are in two situations. If you're in two situations, and it happens quite a lot when training robots, invisible data collection. First one is invisible data collection. Data collection is impossible. We can get all possible combinations of state and action of robots, right? We do not have enough amount of digitalized robot training data, in contrast to videos, which, we have digitalized RGB videos on the web, in social media. The robots, we can't get all possible combination of robot data. That is the one reason. Second reason is non-differentiable output function. We have network's output. That is differentiable, but we need to pass network's output to simulator. That is non-differentiable, so that we have non-differentiable output function. These two makes we need to use RL when training robots. So representative examples are agents in video games and robots. So neural network outputs action that change the environment state. Okay, if non-differentiable, a predefined reward. Okay, so network, we have state out, sim that as in, and network output action that change environment state, that is about this one, sim net as in. It is okay to be non-differentiable because we will apply RL. Predefined reward function evaluate how desirable that resulting state is. So these are three sentences that summarize reinforcement learning. So first, network outputs action that change environment state. That is about this one, network output, and then it is passed to a simulator. It's okay if non-differentiable, we'll apply RL. And a predefined reward function evaluate how desirable the resulting state is. So we have S out. So we try so let's say we have network, and then we have many, so network outputs many possible actions, and then we have many possible S out, and then so we have set of S out 1, S out 2, S out 3. We have many possible S out, and then among these many possible S out, we have predefined reward function that evaluates how desirable the resulting state is. For example, let's say we are trying to teach robots to grasp apple, and then we can maybe design reward function as a distance between robot hand and apple. Among possible state, this one, distance between robot hand and apple might be 10 centimeter, 1 meter, 2 meter. Then this one is desirable, right? The shorter distance might encourage robots to grasp apples properly. Then network, we have predefined reward function and evaluate how desirable the resulting state is. And then we know this one is desirable. Network, and this is also is okay if non-differentiable, it's okay. network is encouraged to repeat actions that lead to higher reward. That needs to be differentiable, and that is usually differentiable. And here, okay, if explicit target actions are not available. So let robots do any arbitrary random actions, and then we have 100 robot actions, and then based on 100 candidates, we have predefined reward function. We evaluate which one is good action, and then let network repeat the desired action again and again. That is the 3-sentence summary of RL. It's very different from supervised learning, right? Supervised learning, network output, just compute loss function, and then backpropagate, that's all. But as the simulator is not differentiable, so we, and then we do not have explicit target, non-differentiable, and then there's no explicit target, so we bypass this kind of backpropagation with RL. Let robot do anything, any action, and then we have 100 action. Let's say we have 100 actions, and then among 100 actions, there can be some good status that we want. And then we encourage the network to repeat the actions that leads the higher reward, and repeat and repeat. That is the 3-sentence summary of RL. Is okay? So problems involving an agent interacting with an environment which provides numeric reward signal, and always learn how to take actions in order to maximize reward. And this is a typical diagram of RL. Agent might be a robot or human. Environment is usually our physics space, or in case of game environment. Action might be for robots, maybe turn right, go straight, or turn left, go straight, such kind of action. State is the 3D rotation of joint maybe, and position. So there's the typical diagram of RL. Agent do action, and then it changes the environment. And from environment, we can calculate reward, and then this reward can be used to update agent, and there's a cyclic relationship between agent and environment. Let's see some example. So this is one of the typical example of reinforcement learning, beginning example, cart pole problem. So we have this kind of car, and this is ground, plane, and then we'd like to move this cart so that the pole is straight. That is our objective. Balance the pole on top of movable cart. That is our objective. And possible states are angle, theta. We have angle, theta, angular speed, position, horizontal velocity. There might be state of cart, right? So cart is agent. Here, this is agent. And action is horizontal force applied on the car. So here, this is the action. In which direction and how much force we need to apply to the cart to make the pole balanced. That is the action. And reward, maybe that is designed by human, heuristically designed by human. 1 at each time step if the pole is upright. So that makes sense because we want pole to be upright very long time, right? So 1 at each time step if pole is upright, so that the outer environment will try to maximize this reward. That means pole is balanced long times. So that is our reward. So that is the one example of our formulation. Objective is balance the pole on top of a movable car, and then state is angle, this theta, angular speed theta, and position, this cart position, horizontal velocity. These are state, and the action is which literal action. What this cart can do. Just move horizontally, right? So horizontal force applied on the car, that is action. And the reward is we'd like to make a balance on pole on top of movable cart. Based on this objective, reward is predefined by human. It is heuristically predefined by human. That is the reward function. So if we can maximize this reward function, then we can achieve this objective, right? We can make a balance on pull on top of move of a cart by moving the cart on the horizontal way, right? Or this one, make robot move forward, and state might be angle, position of joints, and action, torque applied on joints, right? It has joint. It is humanoid. It has joints here, joints, joints. It has joints. How much torque applied on joint? That is the action, and reward 1 time step upright, forward movement. That is also defined by human, heuristically predefined by human, based on objective. So our objective is make robots move forward. Then reward might be 1 time step. It needs to maximize reward. So 1 time step upright. So human needs to be upright to move forward, and then forward movement. So in this way, the robot can move forward like this. This kind of game is called Atari game. Atari is the name of company. This kind of arcade style game is often called Atari game. And objectives complete the game with the highest score. And state might be raw pixel inputs of game state, right? Just raw pixel, just screenshot of gameplay. And action, game controls, like we can move the character like left, right, up, down. And then reward might be score. Our objective is highest score and complete the game. So score increase, decrease at each time step, that might be objective. Reward, so that if we maximize the reward, then we can achieve the objective by moving character left, right, up, down, based on state. So from state, the formulation is always, it takes state, and there is some model, and output action. So action is always from state. We have screenshot, that is also very similar to human playing games. We see the game screen, right? From game screen, that is the state, raw pixel inputs of game state. We move the character left, right, up, down, and then our goal is complete the game with the highest score. That is exactly the same how we human play the game. From raw pixel input, screenshot of game. For every input, every frame could be state of our human. From this screenshot, we control character, and then our objective is complete the game with the highest score, so that model takes state and output action. We will see this detail. And goal is a little bit complicated. So objective is win the game. State is position of all pieces. So all the positions of pieces are observable in Go, right? In StarCraft, it is not, all the environments are not observable, but Go, all pieces are observable. So positions of all pieces are state, action, where to put next piece down, and reward, 1 if win at the end of game, 0 otherwise. I don't think that makes sense because the gameplay could be very long. And this is roughly saying reward can be 1 if win at the end of the game, 0 otherwise. There can be many possible reward design. And reward design is very important when trying RL. Maybe, I think all of you know AlphaGo, right? AlphaGo is based on RL. AlphaGo was happened in maybe 2016. I was graduate freshman when AlphaGo came out, and we have many funny discussion with our lab mate. We have a bet, and I bet AlphaGo will, of course, beat human player. And that happened, right? In 2016. These days, it improved much more, and then our things are changed a lot. So anyway, so AlphaGo is based on RL, and that is also the same. It is gameplay, and we cannot get enough amount of training data so that we can use RL to train an agent that plays Go game. So far clear? So it might be a little bit unfamiliar for you. So I think this 3 sentence is a good start point to understand why we need RL and what is RL. What is difference between RL and supervised learning? Supervised learning, output using neural network, and then compute loss function between output and target, backpropagate, that's all. But RL, we do not have explicit target because of data collection difficulty, and these are non-differentiable. So we have two challenges when trying RL. So instead of trying supervised learning, we have neural network that outputs diverse actions from the same state. From the same state, it can produce diverse actions, and then among diverse actions, all the diverse action changes state, right? Yes, right? So we have S in, network outputs many possible actions that goes to simulator, and we have S out, right? And there can be many possible S out, S out 1, S out 2, S out 3, S out 4, and we measure. We have reward function. We have reward function which measure which one is good. So we have predefined reward function to evaluate how desirable resulting action state is. So among these many possible states, we choose this one. This one is the best one based on our predefined reward function. And then we have corresponding action from network, right? And then we encourage network repeat this action when S in is the input. That is how RL is doing. So in this way, we can avoid two things. We do not use explicit target. In supervised learning, in supervised learning, loss function might be action. Loss function might be this one. If we have explicit target, then we can compute distance between estimated action from network. So let's say action head is net S in. So a action head is estimated action from network, which takes state in. And then if we have ground truth action from S in, then we can simply compute loss function between estimated action and ground truth action, and then do supervised learning, typical supervised learning. But the problem is that we do not have explicit target. We do not have this one. So that this kind of supervised learning is not possible. And we need to use the simulator to make it constrained by physics. And then the simulator is not differentiable, so that we in S out, or the other loss function might be loss S out. Another loss function might be comparing S out ground truth, but S out is also non-differentiable because we have simulator, which is non-differentiable. This is also not applicable, right? We do not have explicit target. The simulator is not differentiable, so we can't try this kind of supervised learning approach. So instead of doing such kind of thing, we let network outputs many actions, and then each action changes state to S out 1, S out 2, S out 3. And among many possible states, we evaluate each state based on a predefined reward function and how desirable the resulting state is. And then we have a state that have maximum reward among 100 candidates. Then we encourage network repeat this action 1, again and again, action 1. That is how we avoid this kind of explicit target problem and non-differentiable problem. That is the RL, and these are some examples. And the reward is based on our heuristic. Based on objective, we predefine and heuristically design reward function. And state is the state of agent. Action is what agent can do. Based on state, the problem formulation is always state, model, and action. So from current status, current angular speed, position, horizontal velocity, we can apply the action. Let's say theta is very big. In state we have angle, right? If theta is very big, then we need to apply f in this direction, right? If theta is positive and too big, then we need to apply f in this direction. That makes sense, right? That makes sense. From state theta, we need to, from S we can guess which action we need to apply, right? When theta is positive and very big, then the desired action should be applying f in this direction, so that we can design some model. We will learn how we design the model later, but we can formulate problem like this, or this one as well. This is, very similar to how human play the game. From screenshot of the gameplay, we know how to control the characters in game, and Go as well. And this will be a little bit mathematic, but not very complicated. So how can we mathematically formalize the RL problem? This is typical diagram of the RL. Agent to action and changes environment. And then this is very, strong assumption. But, to make problems simple, people often assume Markov property, which says current state completely characterizes the state of the world. This might not be true in many cases, but it can simplify the problem setup so that we can study RL more easily. This is assumption, Markov property. Current state completely characterizes the state of the world. And there are some concepts that can be used to define RL problem, as is the possible state. Let's see the cart pole problem. Possible state might be theta. We learned this one, right? Theta, angular speed, position, or there can be many things. Action, how much force we need to apply, right? Force, distribution of reward given state action pair. Maybe one if the pole is on the upright or zero otherwise, we can design this kind of reward function. And transition probability, distribution of our next state given state and action pair. So given theta and f, and then this one, maybe next. The probability of transition between these two states, we can define such kind of transition probability, and discount factor, we will learn this later. So this kind of 5 things can simply define our problem. And that is based on Markov property. Current state completely characterizes the state of the world. At time t equals to 0, environment sample initial state, because we do not have any states in the time step 0. And then until done, we repeat this. Agent select action AT, environment sample reward function, environment sample next state, agent receive reward RT and next state RT. We keep repeat this, doing it again. That makes sense. From state 0, action select action AT. That is, and then environment samples reward. Now we have ST and AT, so that we can get reward. And the environment sample next state, ST, we have ST and AT, we have next state. And then agent receive reward, the next state. We keep repeat this, doing it again. And the important thing is that this one, agent select action AT. How can the agent select desirable action? How can we design agent to select a optimal action? That is policy function, a function from S to A that satisfies what action to take in each state. That is this one. I introduced this one, right? State, model, and action. From state, a policy model or policy network outputs action. That is the policy pi. Objective is find policy pi star that maximize cumulative discounted reward. That is mathematical, that is our problem. How can we get optimal Polish network, pi star, this one, that takes S and output A, that maximizes cumulative discount reward factor. So here we have this one, discount factor. This one is just a hyperparameter constant, usually 0.9 or 0.999. This is just a hyperparameter, and this is reward. We have reward, right? We have reward. So that this shows that reward at the future time step is discounted. Because future, there are so many ambiguity. So that we discount reward at the future time step, and then we give a high weight at the reward from the close time step. That is the discounted reward, cumulative discount award. Objective is find the Polish network, this Polish network that takes state S and output action A, and then from S, how can we design a model that outputs good action? That is always problem. You can visit this example. Let's say we are a game player, and then we have this screenshot. Let's say we have this screenshot, and then that is state, right? Screenshot of raw pixel. Action is the direction of game character. So state model. From the game screenshot, there can be some best action that can maximize score and then complete the game, right? And then we need some model that automatically output a good action from game screenshot. And here, how can we get this model? That is the problem. That is the goal of RL then. Find Polish network at pi star that maximizes cumulative discounting reward. That is the goal of RL. How can we get optimal Polish network? And this is called Polish network. It's policy. Policy means a function that takes state and output action. And here, objective is reach one of the terminal states, grayed out in list of number of actions. And these are number of actions, and this is state. Random policy here. So policy is policy. State action. Or phi is a function that takes state and output action, in simply saying. Seeing this grid, we can design some model that outputs a optimal. We have this kind of actions, right? We have 4 possible actions. And from this grid, we expect the optimal policy network to output this kind of action. That is the optimal policy, right? The goal is least number of actions. Reach one of terminal states, least number of actions. So this is optimal policy, which take S, state X, S, and outputs action. That is the policy. And we want to find optimal policy pi star that maximizes the sum of rewards. And how do we handle the randomness? There are so many randomness, right? Initial state, transition probability. And the goal is maximize the expected sum of reward. So pi star, mathematically, the goal is like maximize cumulative discount award. This one, maximize this cumulative discounted reward. This one, the goal is this one. So that we can maximize, we can get pi star that argmax expectation of sum of cumulative discounted reward, where state 0 is from random sampling. AT, this is policy, right? AT is based on ST. ST is from transition probability, right? But formally, we'd like to get a pi star that maximizes cumulative discount sum of reward. And then we can define 2 things. How good is state? How good is state action pair? To this end, we introduce 2 functions, value action, Q value function. The value function at state S is expected cumulative reward from following policy from the state. And the Q value function is a state and action A. So input is different, but this one is almost the same. Condition is different. Condition is different. Condition here is only S, but here condition is S and A. But what we want to get is the same. The expected sum of the cumulative discounted reward. That is what we want for both value function and Q value function. But the value function V, it only considers state. The Q value function, it considers both state and action. Actually, accurately designing such value function or Q value function is almost impossible because there are many uncertainty in future time step, right? But we can design some network that takes state and outputs this sum of cumulative discounted reward, or take state and action and outputs cumulative discounted reward. Anyway, the value function, it takes S, condition on S. It tries to get cumulative discounted reward following policy. And then Q value function additionally take action as a condition, but it also tries to get expected cumulative reward. The same thing, expected cumulative reward. Expected cumulative reward. But near state X, or the state, the condition is different, but what we try to get is the same. And this is a very famous equation, Bellman equation. So optimal Q value function, so this is Q value function. Q value function, Q star is maximum expected cumulative reward achievable from given state action pair. So optimal Q value function is this one that can, maximum value function, right? Maximum, the goal is always maximize this one, right? We always try to maximize this one. So optimal one is max one. Maximize this sum of cumulative discounted reward with optimal policy network pi. And Q star satisfies Bellman equation. So we can rewrite this form like this one. Q star SA is we can say, this is just a rewritten form of this one. Given max pi, given optimal max pi, we can get Q star, and then we can rewrite this one into this one. Reward is from SNA, and then the remaining future time step, we have SNA as a condition, and then we can define as a recursive form, right? The R is from current SNA, but future time step can be, written as a recursive manner, right? We can introduce an additional Q star here, but they are from future state and action. And then we can get maximum value. That is the Bellman equation. So intuition is, if optimal state action values for the next time step Q star are known, then the optimal strategy is to take action that maximizes the expected value of, very complicated, right? So the optimal state action value for the next time steps are known. This one, this optimal state action value for the next time step. Optimal state, this one is Q value, right? Optimal state action value for the next time step is Q value. And this is known. If this is known, then optimal strategy to take action that maximizes the expected value of this one. This one explains the Bellman equation. We can rewrite the Q value function as this one. They can maximize cumulative discounted reward, and then we can rewrite this in a recursive manner like this, so that R is from current SNA, and remaining term, additional term, is from future time step. We have SNA, and then we can get discounted, cumulative discounted reward as a future time step. And then we can use Bellman equation as an iterative update. And if I goes to infinity, then Q will converge to Q star. So that this one is, we can rewrite this Q value function as a recursive manner. And then if I goes to infinity, then Q will converge to Q star. But here is one problem. So now we mathematically have some representation to get optimal policy network. But the problem is that here, it is not scalable. You must compute, this is dynamic program, right? You learn dynamic program in algorithm class. So, this is just dynamic program. But the problem is that for the dynamic program, we need to compute all possible outputs for input combination SNA, right? Dynamic program. This is just a dynamic program. And then to solve the dynamic program problem, we need to compute QSNA for every state action pair. But this is impossible, right? We cannot get all possible SNA. There are too many combinations of SNA. So that if we have a very simplified environment, then we can solve this with the dynamic program. We learned this algorithm class. But in practice, we cannot compute all possible QSA for every state action pair, so that this is not scalable. Solution is use a function to approximate as QSNA neural network. That is Q-learning. So mathematically, we start with this one, right? We start with the objective is find policy network that maximize cumulative discount reward, and then now we introduce Q-value function, and then we use Bellman equation, and then we now have this kind of value iteration algorithm that can solve this kind of Q-value function as a dynamic program. And if I goes to infinity, then Q will converge to Q star. If we can solve this dynamic problem, mathematically good, but the problem is that not scalable. We must compute QSNA for every state action pair. That is not scalable. There are too many possible combinations of SNA. So instead of computing all this kind of possible SNA, we use a function approximator to estimate QNSA neural network. That is Q-learning. Instead of solving this kind of iteration algorithm with a dynamic program, we use neural network as the approximator to estimate QSNA. That is called Q-learning. These days, Q-learning is not very widely used, but this was widely used in maybe 5 years ago, maybe. Very early time of RL, Q-learning was very popular. So Q-learning use a function approximator to estimate the action value function. So we have value iteration algorithm, and then if we try dynamic program, then we can get optimal Q star, but it is not scalable. So instead of accurately computing QSNA, we use neural network parameterized with the theta, which is trained to output Q star. That is the Q-learning. We define Q function, and then we use neural network to learn Q value. And then, in particular, if we use deep neural network to approximate Q function, that is called deep Q learning. Simply saying that this is a Bellman equation, and then when training, forward pass is like this is the ground truth, and this is output, and then we can compute loss function. But here, of course, we do not have ground truth. We do not have ground truth Q value. How can we get ground truth Q value? So target is from here yi. So you can see target is also from network. Because our assumption is that we have some network that try to approximate Q value. Then we can use neural network's output as a target, right? So this is estimated Q value from our network, and then yi is defined as here. As you can see, R is from current state and action, but remaining things are from neural network. So output is from neural network, target is also from neural network. Very different from supervised learning, right? But target is detached. So gradient can be propagated to this one and this one, right? But we detach this one. So gradient do not backpropagate to target, but only backpropagate to output to make the training stable. Actually, this makes training very unstable. If we use network's target as a target of the loss function, then there can be many possible local minima, and the training might be very unstable. But so that makes Q-learning actually a little bit unstable. But mathematically it makes sense. We use this is network's output, and then we try to use network output to approximate future Q value. This is the current one. From current one, we have S and A. We already have S and A. We can compute R from S and A. There is no approximation. We have S and A, right? We have S networks. We have S and A. S and A can be used to calculate reward function at the current time step, but the future time step we use network output to get target. Right? That is very different thing from typical supervised learning. And this one is actual network design to make to achieve the Q learning. So as I said, the input is just a screenshot. There's RGB frames, the height and width, and last 4 frames, and then just a standard convolution layers, and then full contour layer, and then we have 4 possible actions, right? Left, right, up, down. So we have 4 output, 4 actions. And then it tries to output Q value, QSTA1, QSTA2, QSTA3, QSTA4, right? So input is state S. And single forward pass. So in the value iteration algorithm, this one, value iteration algorithm, we need to solve this dynamic problem, which makes very slow, right? We cannot compute all possible combination of S and A. So we do not rely on dynamic program. We just use neural network to approximate a Q value function. And then it outputs something, right? And then it outputs something. This is network's output. And then, so this is output, out. And this is target. Target is also from network, but R is from our reward function. We have current state and action. So then R is from, we can simply compute R from our state and action. And then this one is from neural network's output. So that we can train this neural network. And this is one, some practice algorithm to make the Q learning better. So learning from, to obtain states, the agent must play through the environment, which produce sequential highly similar temporally correlated states, right? So to get state, agent needs to actually play the game. But playing the game means it is in temporal space, and adjacent batch might be very similar because they are in the similar time steps. So the network might be biased to very similar inputs, and they might make training very unstable. So the current Q learning parameter determines next training sample. That can lead to bad feedback loop. So instead of using, followed frames during the gameplay, they try to use experience memory. Simply saying, it just try to save the training item on some memory, and then use them. That's all. So training Q network on random mini batch on transition from replay memory instead of consecutive sample. In one sentence, this one is the experience replay. This is also widely used in early RL. I'm not sure this is widely used these days. So instead of using consecutive frames, always use consecutive frames. It tries to store training batch in the memory and then randomly use such kind of saved memory for the training. That is called experience replay. This is pseudocode of experience memory, deep Q learning. So we initialize replay memory and then play an episode, full game. Initialize state. This one, we have state. And then for each time step of the game, small probability select a random action for the exploration, or select greedy action from current policy. Take action, observe the reward RTN state, and store transition in replay memory. So this is about replay memory. We use some mini batch for the training, and then we store such used mini batch in the memory. And then here, experience memory. Sample a random mini batch of transition from replay memory and perform a gradient descent step. So this one, we use consecutive frames, or this one, with random probability, we use training step from memory that is used in past time step. So maybe very different frames. That might increase the diversity of the training set, and that makes robustness of the deep Q learning network. Actually, when I was a student, that code is open source, so I tried actually this algorithm, and it works well. So at the first time step, early time step, it fails to do some meaningful play. I watched this on my desktop machine, and it was really funny. After some time, it plays like a very expert level. Most of us cannot do like this, right? And funny thing is that it finds some trick to maximize scores. I'm not sure that is included in this video. This one. I also saw this one. So the code was open source, and when I was a student, I just get the code and then run the demo. It was really funny. It somehow finds some tricky way to maximize the score. And so this is the end of today, and we learned very brief concept of RL, and more advanced RL topics will be covered in next semester reinforcement learning lectures. If you're interested in, you can attend the class. Okay, that's all. So it was a little bit intense, but what I'm expecting from you from RL is that, so this class is computer vision, not RL, so you do not have to fully memorize RL details. What I'm expecting from you is that why we need RL and what is the RL in like a 3 sentence. So what is the difference between supervised RL, supervised learning, and RL? That is what I'm expecting from you.